This cube is a sample from the rock formation under the ground where the oil is. Assuming of course that the oil or gas reservoir under the ground is consisted of multiple cubes similar in properties to this cube. Now back to our sample cube. Any single cube under the ground is subjected to stresses, one of which is the vertical stress, caused by the weight of the overlaying rocks and fluids on top of this cube up to the surface. And we call this overburden stress. There are also two other horizontal components of the stresses which are caused by several parameters which we will explain later of course, with one component bigger than the other, so we call the smaller one minimum horizontal stress, while the bigger one we call it maximum horizontal stress. The overburden stress could be simply known by calculating the weight of the rock and fluids above from the surface till our cube. The horizontal stresses calculation is a bit complicated and is affected by three main stresses: the overburden stress itself, the pore pressure resulting from the fluid inside the pore spaces of the rock trying to escape and pushing the rock outwards, and finally the tectonic stresses. In order to explain the tectonic stresses, we need to go back 4.5 billion years ago when the Earth was formed. It may be hard to believe that something as complex as a planet is formed with nothing more but dust and rocks surrounding our newborn star, the Sun. Over millions of years, gravity pulls these rocks together to form the Earth. Back then, our newly born planet was simply a boiling ball of liquid rock with no solid surface, just endless ocean of lava. A young planet called Theia, in the size of Mars, then heads straight to Earth and collide with it, pushing it to its current course away from the Sun, and causes the formation of our Moon. The Moon is formed from the debris blasting out to space from the collision and circling Earth. And while the Moon is being formed, Earth's surface started cooling down and forming its crust. And with any surface that has been cooled and solidifies through time, cracks have been generated. With water introduced to our planet somehow, the shape of surface map we know now started to take place. Now looking at the world's map that we currently know, and if you take away the blue oceans and drain them away from the map, what we will see is not a flat sandy surface as we may think, but rather a very active area with giant mountains and volcanoes, creeks, peaks, and valleys and earthquakes. If we zoom in, for example, in the middle of the Pacific, we can see a massive crack in the crust. This is not the only crack in the crust. As a matter of fact, the crust is all broken down into pieces, and these pieces we call plates. Now those plates are floating over a gooey semi-liquid layer of the upper mantle called the asthenosphere. And in case you don't know, our Earth is consisted of different layers: the core, the mantle, and the crust. Scientists believe the core is mainly iron and nickel, as they are heavier minerals, so they sink down to the core, while the lighter minerals such as silica floats on surface, hence why the crust is mainly silica. The crust, as well as any solid surface of the upper mantle, are called the lithosphere. And the lithosphere is pretty much all the rigid part of the mantle as well as the crust, while the asthenosphere is whatever semi-plastic or plastic or partially melted layer underneath. And when it comes to the crust, there are two types of crust: the continental crust and the oceanic crust. The continental crust, usually thicker and lighter because it's formed from sediment rocks precipitating on top of the oceanic crust. The oceanic crust, on the other side, is usually denser and thinner and lies underneath the ocean. And it's mainly made out of basalt rock, hence why it's denser. And when those two meet, the denser crust sink below the lighter crust and burn out into the asthenosphere. Now this gooey semi-liquid part, called the asthenosphere, is continuously moving due to the convection process, where cold material, as it gets colder, its density increases, so it sinks to the bottom, while hot magma rises to the surface as it gets less dense. This movement is pretty much the drive for the plate movement above. So if we go back to the world plates map, we will find lots of action at the places where the plates meet. And that's where we find all of our earthquakes and where we can find all of Earth's volcanoes, and also where we find most of Earth's active mountain ranges. And the interaction between the plates at the plate boundaries are guided by the direction of the movement of the plates. These directions here indicated by the arrows in this map. And based on the directions, we can summarize all the interaction between the plate at the plate boundaries into three different types. Transfer, and that occurs as the plates slide past one another. Convergent boundaries, when the plates are colliding with each other. Divergent boundaries, when the plates drifting apart. In transform boundaries, as the plates slide past one another, a high pressure and friction happens between the rock, which causes earthquakes. But they don't tend to have volcanoes or major mountain ranges. A famous example of transform boundaries is the San Andreas Fault. The convergent boundaries action will depend on what type of crust is colliding. If a continental crust collides with oceanic one, they call this subduction zone. Here, the oceanic crust being more dense will sink under the continental crust and starts to melt. The molten rock finds cracks to rise through and erupts at the surface, forming active volcanoes. Similarly, if oceanic crust collides with oceanic crust, one of them, usually the older rock, will sink below the other younger one to form what is called island arc. Last convergent boundary scenario would be the continental colliding with another continental, forming mountains, and the prime example of that is India colliding with Asia and forming the Himalayas. Finally, the divergent boundary, and again it will depend on the type of crust. So in case of continental to continental crust, the earth will form a rift zone where the land rips apart, allowing magma to escape, creating volcanoes. Now we have explained the plate tectonics in a nutshell. Back to our main cube, all these plate tectonic movements is going to add into our stress equation the tectonic stresses part. But we will leave this equation to be discussed in details in a separate video. So bye for now, thank you for watching and see you in the next one.